Morning, this is Ms. Billerbeck, and we're going to talk about 7.3 multiplying special cases. First, we're going to talk about a perfect square binomials. Perfect square binomials are two binomials that are identical, a plus b times a plus b, so a plus b squared, and it ends in a trinomial a squared plus 2ab plus b squared. So this is its product. So the product of a minus b squared is a squared minus 2ab plus b squared. So the only difference between these two are the signs. So this sign's identical to that one, and this sign is unchanging. So the other special case we have is the difference of two squares, where these signs are alternating. So we have a minus b, that quantity, times a plus b. So that results in the product of a squared minus b squared. So let's see how that might happen. So if we have a plus b squared, that equals a plus b times a plus b. Now, if we do FOIL, we get a squared and then plus ab plus ba and then plus b squared. Now, if we remember the commutative property of multiplication, it says ab equals ba. So these terms are identical. So then we end up getting a squared plus 2ab plus b squared. So that's one of our special cases. If we do a minus b squared and we do FOIL, that becomes a minus b times a minus b. And when we do FOIL, we get a squared and then minus, whoops, that's not FOIL. So a squared minus ab and then minus ba, and then I have a negative b times a negative b, which gives me a positive b squared. So that's why this one doesn't change. So these two are identical again, so we get a squared plus, whoops, not plus, that's minus ab, so we're getting more in debt. So negative 2ab. So we're adding to our debt. And then plus b squared. So that's why this third term of the trinomial, the sign in front of it is still positive because we have a negative times a negative. Now, our third case of the difference of squares. So it doesn't matter if we have a minus b times a plus b or a plus b times a minus b because of the commutative property of multiplication. So when we do this, we get a squared plus ab, and then we get minus ba, and then negative b times a positive b is a negative b squared. So because these two terms are identical because of the commutative property of multiplication, we have additive inverses, and additive inverses equals 0. So this results then into a squared minus b squared, our third special case. All right, let's do some examples. So we are just going to do the formula. So we could do FOIL, but let's just apply the formula. So the first one was a squared. So we have 3x squared, and we have a minus sign, so this is going to be a minus 2 times a. So if this is a, that's b. So 3x, and then b is 4, plus 4 squared. So that's the formula. So 3 squared is 9x squared minus, and then we have 2 times 3 is 6, 6 times 4 is 24, x, and then plus 16. So that's the answer for that when we just blindly use these special formulas. Okay, so this is A, this is B. So we're going to use 5x squared. We have a plus sign, so plus 2 times A, which is 5x, times B, which is 2, and then plus B squared, 2 squared. So 5 squared is 25, x squared, and then 2 times 5 is 10, 10 times 2 is 20, x, and then plus 4. So that is the answer. All right, here we can make this into a special case by saying 70 plus 1 squared. So this is A, this is B. So we have 70 squared plus 2 times 70 times 1 plus 1 squared. So this becomes 70 squared is 4,900 plus 2 times 70 is 140 times 1 is 140 plus 1. So that gives us 5,041. So 100 plus 4,900 is 5,000, and then we have 41. This one could be the same as 50 minus 2 squared. So we have A, we have B, and then 50 squared minus 2 times 50 times 2 plus 2 squared. So this gives me 2,500 minus, and then 2 times 2 is 4, 4 times 50 is 200 plus 4. So 2,500 minus 200 is 2,300 plus 4 is 2,304. So there we have it. We can just easily calculate something without a calculator. All right, let's find the product of this one. So this one's the difference of squares, where it results in a squared minus b squared. So if this is AB, this is AB. Okay, so we have a squared, which is 2x squared minus b squared, which is 4 squared. So that results in 4x squared minus 16. Simple as can be. Now we can set this one up as 50 plus 6 and 50 minus 6. So we have an A, B, A, B. And one's plus, one's minus. So we can write 50 squared minus 6 squared, which gives us 2,500 minus 36. So that ends in 2,464. All right, so there we have it. Now let's do this last one here. So we have an example to a pixel area with a border. Okay, so we want to find this area right here. So we need to know what x is, and then we're going to square it. So what's the area of the squared image if the border is 704 square pixels and the border is 4 inches wide? So this border between the image and the outside is 704 square pixels. So what we're going to do is take the total area, including the border and the pixels, and then we're going to our border area and the picture, and then we are going to subtract the picture. So we have also, if this is 4 inches wide, then that's 4 inches wide here. So 4 plus 4 equals 8. So then we have x plus 8 squared minus x squared equals 704. So this becomes x squared plus 2 times 8x plus 8 squared minus x squared equals 704. So we see we have additive inverses on the x squared, so those cancel. And this is 2 times 8 is 16x plus 64 equals 704. We use an additive inverse and we get 16x equals, and that becomes 640, divide by 16, and we get x equals 40 pixels. So when we find the area of this, the area equals 40 squared. So 40 pixels squared, which is 1,600 square pixels. So that is the answer for the total amount of pixels. So there you have it. Have a wonderful day. Bye-bye.